Hey you guys, this is Mr. Sal. This is a quick lesson on representations of linear context. Alright guys, so we may have to read this a few times to figure this one out. But again, Courtney is collecting the coins. She has 2 coins in her collection to start with and plans to add 4 coins each week. So the table on this one, at 0 weeks, it said that she already had 2 coins in her collection, alright? So at 0 weeks, she would have 2 coins. From there, she's going to add 4 coins each week. So from the 2, I would add 4, and I would get 6. Add 4 to that, and I would get 10. Add another 4 coins for the next week, and that's 14. Add another 4 coins for the next week, 18, 22, and 26. Well, the graph, here's what we know about the graph, is that the table gives us x and y values in this order. So the x values on the left columns and y values in the right column. There's other reasons for that, but we'll discuss those later. So the x-axis would be time in weeks. And then the y-axis would be labeled as number of coins. After we get this, then all we need to do is to scale the axis. So starting at 0 weeks, I'm just going to say each line represents 1 week. So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 15 on the end there. Now for the y-axis though, in order to show that after 6 weeks it would be 26 coins, I'm going to do the scale on the y-axis a little bit different. I'm going to say that each line on the y-axis is going to represent 2. So that'd be 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and then 28, 30. That's not great, but it'll do. Sorry, it's just more of my handwriting, I guess. And from here, we're just going to graph all of these from the table as ordered pairs. So this is x value 0, y value 2, x value is 1, y value 6, and so forth. So putting these all on the graph, at 0 weeks, there was 2 coins. That would be this point here. Then at 1 week, we get 6 coins. That's this one. 2 weeks, 10 coins. 3 weeks, 14 coins. 4 weeks, 18, 5 weeks, 22, 6 weeks, 26, and then like you guys said, if there was a 7th week on this one, there would be 30 coins. I'm just going to leave that out for now though. Now in this graph, would we connect the points? So just based on what we've learned, you can have half a week, and that's good, but you can't collect half a coin, alright? So in this case, we would not be connecting the line, even though the book is going to show you that they did. From here, we need to be able to write the equation for the number of coins C Courtney will have after W weeks. Take 1 minute with your neighbor and discuss how you would write the equation for this one. I'm going to show you guys one way that I've seen people write it, not only in this class, but the other ones. What do we get? Coins equals the week number, but plus 4. Now, there's more that we would have to add on to this one. This is what we call a recursive function or equation. We're not going to worry about those in 8th grade. All right, you guys are going to see these more in 9th grade. So we're going to do more of what they call an explicit function instead of that recursive way. Here's what we know about this, is that the number of coins is going to equal, again it's based on the weeks, and Courtney is collecting 4 coins every week. So if I took 4 and multiplied it by the number of weeks, that would tell me how many she's collected since the beginning. But in the beginning, she had the additional 2 coins that she had already collected. So this equation should work for any of these values. For example, if I said for week 6, right? Well, that would be 4 times 6 plus 2. So 24 plus 2 would be 26 coins. So in other words, in week 6, you would get 26 coins collected, which again is shown in the table and also in the graph right here. That would be 26 coins for 6 weeks. Now we kind of addressed this in the last lesson, but if we look at this, the way the equation's written, 4 is representing the rate of change, and we already know that it's 4 coins every week for every 1 week. And we can see that in the equation right here, but also in the table between any 1 week. So that would be an addition of 4 coins when we add this 1 week here. But not only here, but also in the table. Again, it's always between these 2 points. So it went up 2 weeks. I'm sorry, up 2 coins for one week right there, okay? And this plus 2 right here, this is how much she started with. Now the reason I'm showing this to you guys is because this is a general form of an equation which we'll become very acquainted with in the future. When we write our equations, we always take the y value, and it should be equal something. There's different ways to write equations, of course, but this is kind of our most general method. The y value in this case, of course, was the c, and then in terms of the x, which was the number of weeks in this problem, we multiplied it by the rate of change. And from here, we would add the starting value. So this is the general form that we're going to be using to write the equations pretty much from here on out, at least in this class. Part C, is this context linear? Use evidence from the context, graph, table, and equation to support your answer. Just take 30 seconds and discuss this with your neighbor. Is this a linear situation? All right, yes. This one would be a linear situation, and for several reasons, all right? In the context, the only thing we need to know is that there's a constant rate of change, which in this case is 4 coins every week. For the graph, it's a straight line. And in the table, we've already shown that it has a constant rate of change between any 2 weeks. And then finally in the equation, that constant rate of change was shown with this 4 multiplied by the w. Number 2, Jack is filling his empty swimming pool with water. That is the next page. The pool is being filled at a constant rate of 4 gallons per minute. Part A, complete the table and graph below to show how much water will be in the pool after 6 minutes. Take a couple minutes with your neighbor and finish these 2. We'll start with the table on this one, and then we'll use the table as ordered pairs to graph the graph. So first off, on this one, it said that Jack is filling his empty swimming pool, which means at time, when it's at 0 minutes, you would have exactly 0 gallons of water in the pool, because it's empty, okay? But then after that, he's filling it at a rate of 4 gallons per minute. So after, we'll show this in the table, after 1 minute has passed, then we should expect 4 gallons to have gone into the pool. So, after 1 minute, you would have 4 gallons. Now we're going to add 4 gallons every 1 minute, and it's just going up by minutes on this one. So after another minute, we'd add another 4 and get 8. And then after another minute, we'd add 4 and you have 12 gallons. 1 more minute, 4 more gallons, 16. 1 minute, 4 more gallons, and then 1 more minute, 4 more gallons. So this is our table right here. which again gives us a bunch of ordered pairs for the graph. So on the graph, just based on the table, the x's are on the left and the y's on the right. So that just allows me to label the axes on this one accurately. So the x-axis will be labeled time. Well, we'll say number of hours, minutes. And then the y-axis is number of gallons. Now that we have these labeled, let's go ahead and scale the axes. So for a number of minutes, we'll say that's 0, and we'll say each line represents 1. So there's 3, 4, 5, 6, 7, 8, 9, 10. And it goes to 15, even though we won't go that high. The scale for the y-axis, I'm going to say again that each of these lines represents 2. So this would be 4. That's as high as we need to go on this one. Now it's just a matter of putting these points on the graph. So at 0 minutes, we had 0 gallons. There's that point. And then at 1 minute, we had 4 gallons. 2 minutes, 8 gallons. 3 and 12. 4 minutes, 16 gallons. 5 minutes, 20 gallons. And 6 minutes, 24 gallons. Last thing we should check on this one is, would we connect the points? Since we can have half of both, we can connect these points. Well, that's a little better. Part B, write an equation for the number of gallons G that the pool will be in the pool after m minutes. Take 1 minute with your neighbor and write this equation. Alright guys, in order to write the equation we only need 2 things on this one, just like the last one. If we can have the rate of change and the starting values, a value for this one, then we can write the equation. And we can see from the context, the rate of change is 4 gallons per minute. And the starting value for this one, it was an empty pool, so there was 0 gallons for that part, right? Alright, so based on the form we've seen, y equals the rate of change times the x value plus the starting value. The y value on this one is represented by amount of gallons, which is G, and this would equal the rate of change, which is 4 gallons per minute. We'll multiply that by the x, which is time in minutes, and then we're going to add the starting value, which is 0 gallons. Now the good thing about this one, when you add 0, you don't really have to show it, but you can. So I'm just going to make that G equals 4m on this one. Part C, is this context linear? Use evidence from the context graph, table, and equation to support your answer. Let's go over that one. So the answer is yes, it is linear. Of course, the graph was shown a straight line, which is all we need for the graph. In the table, it shows a constant rate of change of 4 gallons per minute, and that 4 gallons per minute was shown in the equation as well, with the 4m. And then in the context, it said it was 4 gallons per minute. Okay, so the rate of change is always constant. And part D, compare the swimming pool problem to the previous problem about coins. How are the problems similar, and also how are they different? Just take a minute with your neighbor and discuss that. Alright guys, you should have had some kind of comparison like this one. The rate of change is 4 in both problems. However, in the coin problem, the initial value is 2, while the swimming pool problem has a starting value of 0, which is the only difference from these two. I guess you could say they're comparing gallons and minutes for this one, or coins and weeks for the other one. Alright, part E, how would you change the coin context so that it would be modeled by the same equation as the swimming pool context? So just real quick, the coin one, the number of coins was equal to 4 times the number of weeks plus the 2 coins you started with. Yeah, if we and the coin problem. If the coin problem started out with 0 coins, then it would be modeled by the same equation. It would have been the coins equals 4 times the number of weeks. And then we would not have added 2, we would have added 0 like we did in this last one. So part F, how would we change the swimming pool context so that it could be modeled by the same equation as the coin context? Yeah?
Start with 2 gallons.
Very good. Just start with 2 gallons, that's it. Number 3, an airplane is at an elevation of 3,000 feet. The table below shows its elevation y. For every 2 miles x it travels. Part A, complete the graph to show how many miles it will take for the airplane to reach the ground. All right? Take 1 minute to finish this graph with your neighbor. All right, guys, here we go on this one. We'll just identify the ordered pairs from the table. At 0 miles, you have an elevation of 3,000 feet. And at 1 mile, you have an elevation of, that's 2 miles. You have an elevation of 2,000 feet. Let me fix that 3. And then finally at 4 miles, an elevation of 1,000 right there. Okay, so on the graph we need to go all the way up to 3,000. Let's label it first. So again with the table it's always x and y. So x is labeled in number of miles. And then the y is the elevation in feet. Number of miles, there isn't any problems there. I just say each line is 1. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The elevation, I need that to go up to 3,000. That's our highest elevation value. So I'm going to say this is 0. And I have 6 lines on that. So I'm going to just say that each line represents 500 feet. So this would be 1,000. There's 2,000. 2,500 and then finally 3,000 feet. So let's put these points on the graph. Just the 3 that we have. At 0 miles, it's at 3,000 feet, so that's this point right here. At 2 miles, we're at 2,000 feet here. And at 4 miles, we have 1,000 feet of elevation right there. So looking at this, we should be able to figure out how many miles it will take for the airplane to reach the ground, not only from the table, but from the graph as well. I'm going to start with the graph. I can see that it went down 1,000 feet in elevation for these 2 miles right here. But this process repeated. So it repeated the 2 times between these 3 points. So for the next point, it should continue this way, another 1,000 feet for the next 2 miles. So that gives us this point at 6, 0. Which we could put into the graph, the table. At 6 miles, we have an elevation of 0. And also, for this one, we would connect these points because you can have half a foot and half a mile on this. So we'll connect these points, something like that. You can find the rate of change in the table. It went down 1,000 feet. For these 2 miles. So yeah, the final answer for this one is 6 miles. All right then, use the table on the graph to find the rate of change. We already kind of did that on the last one. We already know that it's down 1,000 feet for every 2 miles. But this can be simplified also. It goes down 500 feet for every 1 mile. So this would be technically the simplified form of the rate of change, not only in the table but in the graph. All right, from the rate of change, write an equation that represents this relationship. All right. We'll go through this one. So the elevation which is y values. This would equal the rate of change, which is negative 500 feet per mile. And then would multiply that by x, which is the number of miles. But then in addition to that, we have the initial or starting value at 3,000 feet. So this should be the equation or something like it that we would use for the equation. I explain how the equation can be used to determine how many miles it will take for the plane to reach the ground. All you would do on this one is replace the y value, because that's the elevation, at 0. Because at the ground you're 0 feet from the ground. So that'd be equal to negative 500 m plus 3,000. Then you could use the switch and stay game to solve this. And then x, on this one, x, which is the number of miles, would be 6. So 6 miles.